Wilson-Hartnell Governor. A Wilson-Hartnell Governor is a governor in which the bolts are connected by a spring in tension as shown in this figure. Right. So here these bolts are connected with each other by a spring. Right. In the previous case, Hartung Governor, the bolts are attached to the frame. But here these bolts are attached to each other by a spring. An auxiliary spring is attached to the sleeve mechanism through a lever by means of which the equilibrium speed for a given radius may be adjusted. Right. So there's an auxiliary spring which is attached to the lever by a mechanism, right? Sleeve mechanism. The main spring may be considered. So this is the main spring which is attached with the bolts, and here is the auxiliary spring. The main spring may be considered of two equal parts, each belonging to both the bolts. Right? So this can be considered as two springs. One is belonging to this bolt, and the other one is belongs to this bolt. Right? So here is the line diagram of a Wilson-Hartnell governor. Right? So we'll see how about the motion or movement. Before that, we'll see its a little bit detail into how is it controlling the motion, right? So we'll see in bit detail. A Wilson-Hartnell governor is a type of centrifugal governor used to maintain a constant set speed limit. So this is usual, right? So governors are meant to do that work. It consists of two bell crank levers pivoted in the frame, right? So here it also have two bell crank levers which are pivoted to the frame. The frame is attached to the governor spindle shaft and rotates with it, right? Just like the other governors, the frame is attached to the governor spindle, which is rotate with the spindle or shaft. Each bell crank lever carries a ball in the vertical arm, right? So both the bell crank levers will carry a ball and a roller at the horizontal arm, right? So there will be a roller at the horizontal arm, which will help the movement of the sleeve along the shaft. Two tensile main springs are placed on one on each side of the fly balls, right? So there would be two springs, right? Each is attached to one ball, right? So there are two fly balls, so each spring will be attached to those fly balls. Two fly balls are connected by main springs in an end-to-end manner, right? So these two are connected to an end-to-end manner by these springs. Beside this, an auxiliary spring is connected to the sleeve using a lever for adjusting the main spring tension, right? So beside this main spring, there is also an auxiliary spring which is connected to the sleeve using a lever for adjusting the main spring tension. Same lever controls the throttle valve. So this lever will control this throttle valve, right? So there's a spring attached to this lever, and this one will control the throttle valve. Right? I'll show you the diagram. Speed variation occurs when there are changes in the load driven by the engine, right? So we know that the speed will vary depend on the load of the engine. When the load on the engine increases, its speed decreases, right? Usually, when the load increases, the speed decreases. Hence, the supply of steam should be increased, right? To increase the speed, the supply of steam should be increased to reach the set speed limit, right? Similarly, when the load on the engine decreases, its speed increases. So we know that if the load on the engine decreases, the speed will automatically increase. So we need to control the speed, which means we need to control the supply of the working fluid, right? So supply of the steam should be decreased to reach the set speed limit. So this is how the governor controls the speed limit based on the load change. The governor automatically controls the supply of working fluid to the engine with the varying load conditions and keep the mean speed within the set limits, right? So by doing this action, by supplying extra fluid when the speed is low, and by reducing the working fluid if the speed is high, this is how the governor controls the speed of the engine, right? So let's see the working model of this governor, right? Wilson-Hartnell governor. So here you can see those parts, right? Parts of this Wilson-Hartnell governor, and here is a mainspring, right? So there is two mainsprings. Each mainspring is attached to the ball. This is mainspring 1 and this is mainspring 2, right? So this mainspring is attached to this fly ball and this mainspring is attached to this fly ball, right? And then we have vertical arm, okay, vertical arm. And here is the frame, okay? So with this frame, this shaft is connected, and therefore when this shaft rotates, this frame will also rotate, right? And this is our vertical arm, here is our horizontal arm, okay? And this is our pivot, right? So based on this pivot, this may either move this way or move this way, right? So either it can be this way, right? Let me draw like this, something like this, or the other way, like this and like this, right? So either it can move this way or this way, all right? Sleeve, and here's a sleeve which will move up or down depend on the motion of this board. And here is a roller, right? So this roller will help the sleeve to move up or down. And main spindle shaft, here is the main spindle shaft, and the frame is attached to this main spindle shaft, right? And here is the stop, right? So here is the control for the sleeve, right? Sleeve movement. Here is the stop, okay? And here adjusting screw, this may used to adjust this spring tension. And here is the auxiliary spring, right? So this auxiliary spring is attached to this bell crank lever. So not bell crank lever, right? This so bell crank lever is this one, right? Here is the bell crank lever. The board is attached to this, and this auxiliary spring is attached to this lever, which controls the throttle valve, right? So by the motion of this lever, this throttle valve is controlled, right? So either it can open or it can close, depend on the necessary. And here is the input shaft and the bevel gears, right? So input shaft, depend on the motion of the input shaft, this bevel gears will rotate. Depend on this motion, the shaft will rotate. Depend on the motion of the shaft, this frame attached to the shaft will rotate. And therefore, these bolts will either move outside or inside. Based on that, the sleeve will move up or down. Based on the movement of the sleeve, the lever, right? This lever may move up or down. And based on that movement, this throttle valve can be either opened or closed, right? So we'll see how about this motion, right? So how will it motion? So here you can see a kind of a 3D view, right? So this is how the 3D view will look like, right? Now we'll see how will it function, right? So this is how the function of this Wilson-Hartnell governor is. The vertical arm with fly ball expands by pulling the two main springs, right? So by pulling the springs, these arms will expand, right? So this ball will move that way, this ball will move this way, and this spring will expand, right? Two main spring, and the horizontal arm pushes the sleeve upwards, right? And due to this motion, right, since this ball move that way, what will happen? This horizontal arm push the sleeve upwards, right? So when the ball move this way, the horizontal arm will come like this, and the sleeve will move upwards, right? And pulls the lever, right? So when this one move upwards, this one will also pulls this lever, okay? So when this one pulls the lever, this portion, right, the lever along with the roller follows the sleeve to actuate the valve disc, right? So when this one move upwards, this will actuate the lever, which will control the flow of the fluid, right? So you see here, so when this sleeve move up or down, this lever will also move up or down, which will control the motion of this valve, right? So there's a close look of this uh, mechanism, right? Right. So you can see when the sleeve move upside, the lever move downside, and when the lever move downside, which will control the flow of the working fluid, right? So here you see the spring expands. So here shaft, input shaft rotates, the bevel gear rotates. Based on the rotation of the bevel gear, the arm, sorry, shaft rotates. And based on the rotation of the shaft, the frame which is attached to the shaft will also rotate. And depend on that, the motion of the ball wheel, right? So arms expand due to centrifugal force produced by the rotating flyballs, right? So due to the centrifugal force, these arms will expand. Right? These arms will expand. Arm contracts and come down due to the recoil force of the spring. Right? So when the spring pull it back, these arms may come down, come closer. Input speed from engine that is to be controlled is applied to the input shaft. Right? So here is a shaft. Right? So there would be an engine which would be working. So depending on that motion, this shaft will also rotate. When engine speed increases, arm expands, right? So when the speed increases, we know centrifugal force increases and the arm expands. And if the arm expands, this sleeve will be lifted up. If the sleeve is lifted up, this lever will also be lifted up. If lever will be lifted up, then this will come down, right? Arms expand and pulls the sleeve upwards, which in turn rotates the lever to close the valve, right? So which will come down and this will close the lever, close the valve, right? So if it closes the valve, what will happen? The fuel supply would decrease, working fluid supply would decrease, and therefore it can reduce the speed. Right? So upwards, which in turn rotates the lever, close the valve to decrease the output flow. Right? So when the output flow is low, the speed will automatically be reduced. Valve closes to decrease the output flow. Right? The other way is also true. When the engine speed decreases, right? When the engine speed decreases, arm contracts, right? This arm contracts and pushes the sleeve downwards, which will lift the lever up, right? Which will open the valve, right? So which will open the valve to increase the output flow, right? So when it opens the valve, the output flow would be increased. Okay, at this position, we see the sleeve is lifted, I mean not lifted, this is pushed down, so the lever is lifted up, right? So if the lever is lifted up, the flow is now open, so the working fluid may increase. So which means when the working fluid increases, the speed will again increase, right? Why? Because already the speed is decreased, and that's why this phenomenon is. So since the speed is decreased, we need to increase the speed. So working fluid will increase, the flow of the working fluid will increase, which will in turn increase the speed, right? So this is how the Wilson-Hartnell governor functions. So when the speed increases, you can see the bolts are flying apart, and when the speed is down or low, the bolts are close to each other, right? So by this motion, the lever is actuated, and based on that, this flow of the working fluid is controlled. Now we'll see how to solve a numerical if it is given, right? If you need a Wilson-Hartnell governor. Okay. So these are the terms we use in the Wilson-Hartnell governor. First, P, that is tension in the mainspring, right? So P, which is the tension in the mainspring. S, tension in the auxiliary spring, right? So S is tension in the auxiliary spring. Okay. Small m, mass of each ball, right? So this is mass of each ball, and capital M is the mass of the sleeve, right? And SB, stiffness of each ball springs, right? SB is stiffness of each ball spring, and SA is stiffness of the auxiliary spring, right? SA is the stiffness of the auxiliary spring. And FC is the centrifugal force on each ball, right? So FC, centrifugal force on each ball. R, radius of rotation, right? R, radius of rotation. Okay. So now we'll see how to solve if any numerical is given on this topic. Now total downward force on the sleeve. So we will see here is our sleeve, right? Total downward force on the sleeve is equal to mg. So that's the mass of the sleeve into its gravity, that is mg, plus s, right? S, that is spring, auxiliary spring force s into b upon a, right? S into b upon a. Why b upon a? Because here's a fulcrum, right? So the force would be b upon a, right? It will be divided in ratio to this arm. So this S into B upon A, right? So here's a fulcrum. So if we say, for example, if we take a moment about this fulcrum, this force into A will be equal to this force into B. So based on that, we can calculate how much is the force exerted by only this portion, right? So which will give you S into B upon A, right? So this is the total mass or total force act on the sleeve, right? So now we'll solve it by taking moments about point O, right? So as like we have done for rest of the governors, we'll take moments about this fulcrum point O. So if we take about point O, okay, so we will have Fc, that is centrifugal force. Then we have spring force P, okay, and then we have mass or weight of the sleeve, right? So Fc is in anti-clockwise direction. Force by the spring is clockwise direction, and force by the mass is again clockwise direction. Okay. So if we take about moments about this point O, we'll see Fc minus P into X, right? Fc minus P into X. Why? Because Fc is centrifugal force acting this way, P is the spring force acting that way. So Fc minus P into length X will be equal to mg plus S into B upon A by 2, right? So here is the downward force on the sleeve. So this is the downward force on the sleeve, right? Mg plus S into B upon A. And we are dealing only with the half of the system, right? We are dealing only with the half of the system, right? And that's why this 2 is, right? Mg plus S into B upon A by 2, right? So another B upon A by 2 would be on this portion, right? Into Y, right? This is Y, this is the Y, okay? This is Y. So this is X, this is Y, okay? So these are the two forces acting on the acting from the point O, okay? So from this we can find the whichever the quantity is asked, right? So this is for the mean position or at the equilibrium mean position. So now we have to find, or we have to modify this equation to find if the ball is rotating at maximum or minimum position, right? So we know if it is rotating at maximum position, the ball will be somewhere like this, okay? If it is at minimum position, it would be something like this, right? So first we need to give some notation for that. So usual notation we know it is suffix s, suffix 1 is for minimum and suffix 2 is for maximum, right? So I'll replace this equation with suffix 1 to get an equation for the minimum position. Let suffixes 1 and 2 be used to denote the values at minimum and maximum respectively, right? So minimum 1, maximum 2. So suffix 1 is minimum, right? So I'll modify this equation with suffix 1. So Fc1, right, centrifugal force 1 minus P1, right, minus spring force 1 into X won't change, equal to mg, that is same sleeve mass, into S1, right? So that is auxiliary spring, that's force S1 into B upon A by 2 into Y, right? So Y won't change, right? Why? Because usually we neglect this obliquity effect, right? So while this ball moves that way or this way, there will be a small change in this height, right? If you draw a curve, something like this, there would be a small change in this height, but we will neglect it usually if it is not provided to consider it. So usually we neglect it. Similarly, at maximum position, right? At maximum position, so we use suffix 2, right? So this equation, I will use suffix 2 to write the equation for the maximum position. So Fc is already there, so Fc2, that is centrifugal force 2, minus P2, right? P2, that is force at the ball, equal to into X, right? Into X, that is this length X, is equal to mg, right? Capital mg into plus S2, right? So that S2 is the spring, auxiliary spring, that force at maximum position, right? Auxiliary spring force at maximum position, that is S2 into B upon A by 2 into length Y, right? So I just modified this equation with suffix 1 for minimum and suffix 2 for maximum, right? So now we can write or found the equation for the minimum and maximum positions, right? So now we'll see how to solve them to obtain the value, okay? Now subtract the equation 1 from equation 2, right? Say for example, if we want to find the range, then we have to find these values exactly, right? So we'll solve it now. We'll subtract this equation 1 from this equation 2, right? Okay, subtract equation 1 from equation 2. So what will be having? FC2 minus FC1 minus P2 minus P1 into X, right? So FC2 minus FC1 minus P2 minus P1 into X will be equal to this side mg by 2 cancelled out, right? So S1 into B upon A by 2 into Y, no, S2 into B upon A into Y minus S1 into B upon A by B upon A into Y by 2, right? So only this term is remaining, right? So that is S2 minus S1 into B upon A into Y upon 2, right? So S2 minus S1 into B upon A into Y upon 2, right? So this is the equation we obtained by subtracting 1 from 2. Okay. When the radius increases from R1 to R2, right? So when the radius increases from minimum position to maximum position, right? So that is R1 to R2. The ball springs extended by the amount 2 into R2 minus R1. So we know the extension is R2 minus R1. Why? Because initially it was at R1 and now the extended length is R2. So the extension is R2 minus R1, right? But since we are considering these two are two springs, right? Since we are considering this as one spring and this as one spring, we will multiply it by 2. So we will be 2 into R2 minus R1, right? So now the radius of the increase can be written as 2 into R2 minus R1. And the auxiliary spring extension by the extended by the amount R2 minus R1 into Y upon X into B upon A. So we need to find the extension of this auxiliary spring. Why? Because when this sleeve move up or down, right? When this sleeve move up or down, there's a fulcrum. So this will either move up or down. So this spring will extend or contract, right? So we need to find that motion also, right? So we know we have already found that for the usual governors, this setup R2 minus R1 into Y upon X, we already know, right? Say for example, we'll take any other governors, right? So we know that just for you to recall, right? Say here H is equal to R2 minus R1 into Y upon X, right? H is equal to R2 minus R1 into Y upon X. Right? So here H is equal to R2 minus R1 into Y upon X into there's a B upon A. Why there's a B upon A? Because there's a fulcrum, right? In the previous cases, we don't have a fulcrum. So here we have a fulcrum. So that's why there is a B upon A, right? So there is a B upon A, which we have to carry here also, right? So usually H is equal to R2 minus R1 into Y upon X. But since we have a fulcrum here, which will be B upon A also. So we need to multiply it with B upon A. So this is the extension of the auxiliary spring, right? Therefore, P2 minus P1 is equal to, so here, what is P2 minus P1? This is P2 minus P1, right? The extension of the main spring. At P2, there is maximum position, P1, minimum position. So we know the extension of the spring is stiffness of the spring into the extension, right? So the stiffness of the spring, ball spring, that is SB, right? Stiffness of the ball spring is SB. And the extension we now found that 2 into R1 minus R2, right? Extension is 2 into R2 minus R1. So the force at main spring is 2 into SB, right? Why 2? There are two springs and each spring, the stiffness is SB into the extension. Extension is 2 into R2 minus R1, 2 into R2 minus R1, which is equal to 4 SB into R2 minus R1, right? 2 into 2, 4 SB into R2 minus R1, right? So this is the force at the primary spring, which is connected to the bolts. And S2 minus S1. What is S2 minus S1? That is the spring force at the auxiliary spring, right? S2 is at maximum position and S1 is at minimum position, right? And we know that force, spring force is equal to stiffness into extension, right? So stiffness of the auxiliary spring is given as SA. Right? So SA into extension will give us the spring force. So S2 minus S1 is equal to SA, that is stiffness of the auxiliary spring, into the extension of the auxiliary spring, which is R2 minus R1 into Y upon X into P upon A. Right? R2 minus R1 into Y upon X into B upon A. Okay. So S2 minus S1, that's the spring force strength or difference in the auxiliary spring is SA into R2 minus R1 into Y upon X into B upon A. Okay. So now we have formulas for P2 minus P1. That is the spring force difference in the main spring, as well as the spring force difference for the auxiliary spring. So what we'll do, we'll replace or substitute these two values here in this equation. Right? So here we have P2 minus P1, so we'll substitute it here. And here we have S2 minus S1, we'll substitute this here. Okay. So when you substitute it, we will have FC2 minus FC1, okay, FC2 minus FC1 minus P2 minus P1. Instead of P2 minus P1, I'll put 4SB R2 minus R1, right? 4SB R2 minus R1 into X, right? Into X equal to S2 minus S1. So S2 minus S1 is equal to SA into R2 minus R1, right? SA into R minus R2 minus R1 into Y upon X into B upon A, into Y upon X into B upon A. Into, right, I just replaced for S2 minus S1. Here we have already B upon A into Y upon 2, right? So that is this B upon A into Y upon 2. Okay. So when we simplify it, we will have FC2 minus FC1 minus 4SD R2 minus R1. I'll take this X the other side, okay? Equal to SA by 2, right? SA by 2, this 2, SA by 2 into R2 minus R1 into Y upon X, right? And I take this X here, so I'll put this X here, okay? I'll put this X below the Y. I'll put this X here, not here, here, okay? So here I will have Y upon X. I have already taken this 2 here, okay? So what will I have? I will have SA by 2, right? SA by 2. This 2 is now moved here, SA by 2 into R2 minus R1, R2 minus R1 into Y upon X, right? Into Y upon X into B upon A whole squared, Y whole squared. There are 2 B upon A, right? So this B upon A into this B upon A whole squared. Y upon X, and I take this X here. So again, there's Y upon X. So Y upon X into Y upon X whole thing squared, right? So FC2 minus FC1 is equal to FC1 minus 4SB into R2 minus R1 is equal to SA by 2 into R2 minus R1 into Y upon X into B upon A whole thing squared. Okay. So you can further solve it, right? 4SB, okay, 4SB, I am dividing the entire equation with R2 minus R1, okay? I'm dividing the entire equation with R2 minus R1 and making this FC2 minus FC1 as the subject, okay? So FC2 minus FC1 upon R2 minus R1, that's here, right? FC2 upon FC2 minus FC1 upon R2 minus R1. I'm taking this one here out, other side of the equal, right? Equal to 4SB. I have already divided with R2 minus R1, so there is only 4SB. Plus, I have taken this term here, okay? Plus SA by 2 into Y upon X into B upon A whole thing squared, Y upon X into B upon A whole thing squared. I have already divided with it R2 minus R1, so there is no R2 minus R1, right? So I'll divide the entire equation with R2 minus R1. Okay, so here R2 minus R1 and here R2 minus R1 and this R2 minus R1 will be cancelled out. Similarly, this R2 minus R1 and R2 minus R1 will be cancelled out. Okay. So what will I be having? 4SD plus SA by 2 into Y upon X into B upon A whole thing squared will be equal to FC2 minus FC1 upon R2 minus R1. Okay, so this is the final formula for the Wilson-Hartnell governor. So you can make any one of this as the subject to find the required data or basic information. Right? And there's not when the auxiliary spring is not used. Okay, there's a condition. If this auxiliary spring is not used, which is the auxiliary spring? This is the auxiliary spring. If this is not used, which means if this setup is directly connected to the throttle lever and there's no setup of this, what will happen? We will have this S part to be 0, right? So SA will be 0. Why SA will be 0? SA is the stiffness of the auxiliary spring. When there is no auxiliary spring, this part will be 0. So if this part will be 0, this SA will be 0, which means this term of this equation will be removed, which means 4SB is equal to FC2 minus FC1 upon R2 minus R1. Okay. So if you want to make SB as a subject, FC2 minus FC1 upon 4 into R2 minus R1, right? So this is how we tend to solve the numerical on Wilson-Hartnell governor.